All right, so you guys doing well on Monday?
Yeah.
Okay. Thank you. Perfect. All right, so let's start the where we left last time before exam week. Once again, we have a plenty of chance later this semester, but you guys, I'm seeing you guys did pretty well anyway. Here's something. So chapter 6, 7, 8, 9, 10, 11. Hopefully we can cover most of the parts in those chapters. So we have another exam maybe next month, November, before Thanksgiving. So that are the findings. So you still have a lot of chance. Oh, one more thing. As you got, if you remember, I'll also give you some extra credit Canvas quiz. So there will be also your practice for your final exam. Because the final exam, because we did at Thanksgiving, right? So you also did on Canvas. So you can also practice your kind of final exam like problems on your extra credit quiz on Canvas during this semester. Okay. All right. So there are a couple of things I want to point out in chapter 6. So here's the first one. There's two main reactions you may see in this chapter 6. The first one is this one, and this is the other one. So if you think about the covalent bond, it's just some small space that can share a pair of electrons between these two atoms in a molecule. The first one is this one. The second one is this one. Okay. So you're going to see the first one is what we call symmetrical bond breaking. This is what we call unsymmetrical bond breaks. Okay. So here's the thing. If it's indeed a pair of electrons here and here, for A and B, we can say they don't have a much difference in electronegativity. Okay? So either A or B cannot have a dominant power to pull those electrons to themselves. So what they do, just do it evenly for each. So one goes on A, the other one goes on B. So when you do this symmetrical bond breaking, you're going to have one electron on A, the other electron is on B. So this is what we call this symmetrical bond breaking. It's symmetrically just bond like in a half and evenly. Makes sense, right? So if that is true, you can see this is different because we call this unsymmetrical bond break. Meaning, in here I made one assumption. That was the B is higher in electronegativity than A. Okay? So B will have a more dominant power to pull those electrons. So not just one, but they're going to pull those two all together on themselves for B. Okay? So obviously, then we'll make this no electrons on A, but B takes all two electrons right here. Makes sense, right? So far so good? Okay. So this is what we call this unsymmetrical bond breaking. Okay. So this is the main reactions that we categorize in chapter 6. The first one, we call this radical reactions. Radical reactions. The second one, we call this polar reactions. Okay? So I want you guys remember this one. Okay? So the first one, symmetrical bond breaks, we call this radical reactions. If it's not symmetrical, one gets all the electrons, we'll call this polar reactions. Okay? Makes sense, right? So far so good. So move on. Okay, if that is true, happen to get some example here. So radical reaction is something you have some compounds over here, but they're going to have odd numbers of valence electrons. So that means it's not going to be one pair, two pairs of electrons on A or B atoms, but maybe 3 or 5 or 7 sort of odd numbers of valence electron on A. Then this is what we call radical compounds or radical elements. So radical, as you can see from this word, is quite not stable. It's very unstable. So most of the time, this will only stay for a few seconds, a short period of time, unless there's very dramatic conditions in keeping this compound in the radical form. Okay, so this is why this becomes also a big major proportion. If you have so many of this one in your body, and animal's body, will damage your tissue too. Anyway, so if this is, do you guys know why this is so unstable though? If it's radical, do you guys remember what we did in Jenkin 1 and 2? Pauli exclusion rule. Do you guys remember? No? Okay, Hund's rule. Kind of. Okay. So whenever you have orbital, max number of electric field is what? 2. Perfect. So because of the orbital and the energy level they need to sustain, and this electrons around the nucleus, the one makes your compound so unstable. This is all you need to know. I'm not going to put it much in detail. But anyway, just remember this is not very common. Anyway, so I'll give you one example. This is methane, right? You guys, I hope you guys remember this. We need take the 4, 3. Okay. Anyway, and you have a chlorine here. You can say put it over here. So what they need to do, obviously these two are same in electronegativity because they're same elements, right? So obviously they're going to do this and this. And also if you look at this one, they're not so big change, big difference in electronegativity of carbon or of hydrogen. They also do this one as well. So for radical reactions, the way I'm using this arrow here is more like this. Okay, so this is what we call fish hook, or some people call this half-headed arrow. Okay, that means this will show you only direction of one electron, not two. So if I do one here and another fish hook over here, each one of the electrons going opposite directions like this. Because once again, the bond is what? Single bond is what? Pair of electron in a small space. So each one goes on each. Okay? The same thing over here. The electron, there are 2, goes in here, another one, the other one goes on here. Okay? So in the certain condition with the light, they do this. So you're going to have this and this one, right? Make sense so far? Okay, good. For this one, we're going to have this radical and this one. Okay, so they're all in odd numbers, 1, 1, 1, 1. Well, technically, this is what? 7, but anyway, it's the odd numbers of the spectrum. So what they do is they try to do radical reactions. Okay, and then outcome will be what? So you can picture this one separately. So you can have this one. So this is just one example of radical reactions. Obviously, you can do, so they can do some other like this one and this one. There are some possible other products, but mainly we're going to have those two here with the radical reactions. Okay. I'll move on. It makes sense so far? I'll move on. So this is just the, this is not very common, obviously, because the nature always they wants to keep themselves in a quite somewhat stable form at least. But radical form is only for a very short amount of time, because the form they can sustain a very unstable form, which is not possible for a long time. So obviously we'll see that means what? We'll see more often polar reactions instead of radical, right? This kind of makes sense, right? Why we see much more this direction. So this is something you see a lot in organic chemistry, especially in the chemical reactions. Before I get into any example of polar reactions, there are certain terms we need to go over to see those in the much detailed information. The first one is the polarity. Okay? So polarity is, I think you guys already learned this so many times in previous chemistry course. This is just being polar, having some dipole moments because you have carbons or other elements attached to it, bonded to there, or carbons or other elements over here. If you look at those one here, obviously now you see the big change, big difference in electronegativity in chlorine and carbon, and also carbon and lithium here. I'm giving you just two examples because I want to tell you, I want to emphasize, this is all about the relative strength or relative electronegativity strength. So in here, chlorine is, so if you look at the periodic table, if it's more on the right side and the top position is electronegative. If it's like somewhere in the down on the left side, that's where you can find the low electronegativity one. So compared to those two elements in the periodic table, obviously this is more electronegative than carbon. Okay, so then you can say some delta sign. So delta sign means it's very slightly, like very small. So delta negative, delta positive means this part of your compound is slightly negative, and this is slightly positive. But once again, it's all about what? Relatively speaking. It's relatively speaking, this part is a slightly negative charge, this part is a slightly positively charged, because they don't share the same electronegativity. They don't have the same power to pull the electron to themselves that makes the change in electrical potential on two different atoms in the molecule. That makes this compounds polar. Can that make sense, right? Okay. So if that is true, is the carbon always going to be positive? That's actually not here, because all the metal ions, the metal elements will become more lower in electronegativity, even lower than the one of carbon, right? So if you look at this one over here, this is where you can find the slightly positive charge, and now this is slightly negative charge. Okay, so this is good example, good compounds that we may see in your polar reactions, as you're seeing some polarity in compounds. They will show you something weird. I'll show you in minutes. This is something what we need to do. Okay, so now we know what polar compounds become and how it happens and so forth. But before I move on to example, a few more things I need to tell you. So besides this polarity, there's one more thing I want to tell you is polarize and also ability. So it's polarizability. So literally what it says is polarized is not themselves being polar, but they're kind of forced to be polar by something else. And the ability is just the degree or the measure of their being polarized. So it's a similar concept to polarity. So polarity is the one that does the elements showing different electronegativity being dipole moments of polar. This is the more like a passive form. This is similar to the polarity, but this is the tendency of the elements to be polarized by others, not for themselves. It's more like active here, right? Polarity. This is more like a passive form. So if you look at the definition of the textbook, it's like external electrical field applied to the conditions, and those molecules become polar, and how polar it can be is the polarizability. So if it's high in polarizability, they'll be easily polar by external electrical field. So what they're really saying is this one. So you have elements in the compounds. You normally keep them in the solutions, right? Or some other gaseous form. That means you have other surrounding molecules. We call this solvent molecules, right? And then if your solvent molecule is polar, like water, or if there's some charged ions like metal ions and anions and stuff, in the nature of anything in the universe, they're always moving. They're not. So this one, if you look at this one, they just seem still, right? They don't do any motion here. They slightly move anything. But they actually continuous moving at atomic level. We just don't see it. It's very small distance they're just moving always. Anyway, so if that is true, it is continuously moving. So there will be change in electric potential within your unit space. That will generate the electrical field in here. This is something we just need to memorize. Any physics major here? No? So anything that charged molecule was charged beam moving in the space, they can make some electrical field. So this is how external electrical field generated and applied to this molecule. And if those two molecules being more, so they can be polar by those electrical field, that means they have a high polarizability here. If it's not, they're very low in polarizability. Okay, yeah. So I'll move on. I'll tell you, okay, I'll give you one example here. I'm telling you this because there are some exceptions for this one. So to be polar compounds, I just told you there has to be different in electronegativity, right? All right. But if you look at the this one, those two, carbon and sulfur and iodine, are same in electronegativity. Or we can say similar, very similar in electronegativity. There's not much difference in electronegativity, meaning electropotentials. So technically speaking, following this rule, they should be nonpolar, right? They should be nonpolar. But this is exception. Those two will be slightly negative, and this is slightly positive because of polarizability. So once again, it's not because of these two. It's because of by something else outside. And also these two, if you look at the sulfur and the iodine, sorry, iodine and the periodic table, you can definitely tell they're much bigger in size, right? It's much in lower position. You see that, right? Yeah. So that means what? They have a much bigger space to store more numbers of electrons. And most outer shell, they have some electron they can move or use to make bonds or some chemical reactions here. And carbon is, relatively speaking, much smaller and tightly compact electrons around it in the nucleus of the carbon. So when you apply some external electrical field on these compounds, they have a much ability to move the electrons around themselves because they're bigger in size and they're more loosely held by the nucleus. That means the electrons are more available on here and here than carbon. That makes these two polar, even though there's no change in the electronegativity. This is exceptions. This is happening because of the polarizability. They're much higher in polarizability than carbon. That's why, relatively speaking, maybe not a lot, but being polar, even though there's no change in electronegativity in those two. Just exceptions. I don't know, do a bunch of equation here, but you'll see more of this often for sure. But this is something you may want to keep in your mind. Okay, I'll move on. Okay, so that makes sense though, right? Okay. All right, if that is the case, now there's one more thing I want to cover. I promise. One more thing. I will move on to the next point. So polar reactions. There's two things you need to know. You need to identify two things in these reactions. The first one is nucleophile. The other one is electrophile. Okay? So nucleo means nucleus. So if you remember, nucleus is just made of protons and neutrons. So simply it's positively charged. So this is a positively charged nucleus. Phi is loving. So they love to find the nucleus. They love to find the positive charges, being particles. That's what it means. So the nucleophile always look after positive ones. They want to go to the positive ones because they love nucleus. Because nucleus is positively charged. Electrophile is opposite. They love electrons, okay, which is negatively charged. And also they love electrons because it's electron-loving compounds. So they're always going after something that is negative, something more electron-rich compounds. These are the ones you need to identify first whenever you do some polar reactions in the chemistry. Okay, makes sense, right? There's two. Okay, good. So you're doing so far so good. That's very good. Nice. So here's the thing. One of the examples I gave you 2 weeks ago before the exam was this one. You have ethylene, or you can call this ethane. Either way, it's fine. And hydrobromic acid here. So this is a typical addition reaction we cover in the first part of the chapter 6. Let me just remind you of this one. This is double bond. Double bond is made of what? 1 sigma bond and 1 pi bond. Perfect. So let me read this one real quick. This is a double bond here, as we saw in your exam 2. Okay. This will be sp2 because they're going to keep one of each carbon here as what? Pi bonds. It looks like this. Pi bonds right here. Okay? So you have a sp2 hybrid sigma bonds are between these two carbons here and those hydrogens. But there are additional bonds we call pi bonds, where you can find a pair of electrons, one from each carbon. So that's why they only headed to sp2, not sp3. So here and here. Okay. So as you can see in this structure, the ones in the sp2 hybrid orbitals, we really can use them all because they are tightly bound to the nucleus and the carbons and hydrogen and so forth. And also they point it in the very center point of your bonding here. But if that is true, the one on the electrons on the pi bonds up and down, they're away from the central bonding. So they're more accessible for others to pick up or to use for these compounds. So those electrons are more usable or accessible compared to the one in the middle. Make sense? So good? Okay. So if that is true, I'll show you just one thing on this one. Okay. So if that is true, you have this one, and you know this is much more electronegative than hydrogen here. So it's not going to be radical, but this one. So whenever I do this, now unlike the fish hook half-headed arrow, this is the full-headed arrows. Meaning it's the motion or the direction of the two electrons, whole, the pair, not just one. because it's now heading, it's full headed now. Okay, so that means those 2 electrons are now on bromine after bond breaking. So there will be no electrons on hydrogen. There will be 2 additional electrons on here, and as you know, there are already 3 lone pairs here. This is group 7, right? So now it has 8 instead of 7, but bromine is group 7. This is negatively charged. The hydrogen is group 1. It should have at least 1 electron to be neutral, but now they got electrons stolen in the bond they share. So there's nothing here. So there'll be 0 electrons available instead of 1. It's positively charged. It's missing 1 electron. Makes sense, right? Okay, good. So here's the thing. If that is true, this is something that is positive. Something that is positive. And this is something that is negative. Obviously, to be neutral, they need to look after something that is negative, right? When you're positive, you want to be neutral, you need to find something negative, right? So this is what I mean by electrophile, what we just mentioned. Make sense, right? Okay. This is negative, so you look for something that's positive. So we call this nucleophile. Okay. So if those are true, we have 2 available nucleophile and then neutrophile. So here's the thing. Like I mentioned, the one in this one in the pi bonds. Maybe you can. This is this one. I'll try to use this one because this is more available. They actually can kind of work as like a nucleophile. So they try to look for something positive here. So this is the one we can use in the pi bonds. Goes to this one. Okay. So if that is so you see this is gone. There's electrons here to this electron right here. We send it to something to get the electrons here. Okay. So if you redraw this one, there's the here. This one. Okay. And now there's only one single bond because there are only sigma bond now. They use the one on this pi bond is used up to make the single bond to hydrogen, right? The pair of electrons goes to there. So now this hydrogen has 1 electron now. Once it's positive, now it's neutral, right? Good. And now it has 4. So that's good, but the problem is their double bond is gone. To make the single bond to the proton, which is the hydrogen, there are only 3 electrons around this carbon, the other one, right? See, but there was double bond here, so it's a 4. It was no problem. But they used the pair of electron pi bonds, breaking the pi bonds. They just only have a sigma bond, which is single bond here. So only 3. So the carbon is group 4, but it only has 3 electrons around the carbon. So it's going to be positively charged, right? Positive charge, because they lost now double bond here. We call this carbocation. Okay? This is like a cation, like a positive charge ion kind of carbon is in here. So this is also look for something that is what? Negative. Okay, so this will become also electrophile. I mean this carbon right here. And then this will look for something that is negative. Right? So actually there's a pair of electrons here will go to this carbon right there. So they're kind of donating the pair of electron to this carbon cation. Okay? So now this bond, and here 1, 2, here it's 2. Okay? So if you rewrite this one, so now you have a bromine now only has 3 lone pair, and there's 7. This is neutral now. This carbon also happy because now it is 1 electron in the carbon. So this is also neutral. So this is what we did in the first part of the chapter 6. It's a good example of addition. Kind of make sense? We good? Okay. Let me do one more. I will do one more. Let me actually give you one. Just brief. Very brief. If you have nitronium ion either, it would be electrophile or nucleophile. This is positive, right? So yeah, perfect. We will look for something negative, right? So they love something is negative, perfect. So it will be electrophile. Makes sense, right? Okay. So if you have trimethyl sulfonium ion, like okay, so it's positively charged. This will be also nucleophile. So how about this one? Cyanide anion. Okay. This will be now then nucleophile. So that's pretty much it. This is all you need to know. When they're bond breaking, more electronegative atom will take them all, or a whole pair of electrons, right? And they become nucleophile, or the other one will become nucleophile, so forth. See how what might be the charge, former charge on this atoms. Okay. Let's do one more. This is a bit different from what we just did. Okay. Okay. So if you look at this one over here, this one is the bit weird. So it has 1, 2, 3, and there's 1 lone pair on this carbon, 4 and 5. So instead of 4, it has 5. That's why it's negatively charged in this carbon right now. We call this carbanium. So it's like a carbon cation, but it's the other way. It's like a negative charge is the positive charge. Okay, like an anion. Okay? And then if you look at this one here, once again, this is going to be polar, like an unsymmetrical bond, right? Bond breaking, right? So this will go to bromine for sure, right? Because this bromine is more electronegative. Okay, and this one right here will become this, because now it lost all the electron on their share in the bonding for carbon. It's gone. So it's only 3. 1, 2, 3. So this is carbon cation again. Okay, makes sense, right? So this is electrophile, and this will become nucleophile. Okay. Then here's the thing. This is negative charge, so you'll be electrophile and nucleophile. Nucleophile. This is a nucleophile, and then this is the main key actually. Whenever you do this, so you do break the bonds based on which one is more higher in electronegativity. That's the first one. But once you do that all, see the formal charge on those ones and see if it's going to be electrophile or nucleophile. And now you need to do some chemical reactions. But now you need to do this will they have a pair of electrons in lone pair, which is also available, usable for bonding. So either this one going to take this one or this one, that's the question. What you're gonna choose. This is negatively charged nucleophile. This is carbon cation, something looking for something negative. This is for something then looking for something positive. Which one is better for this one? Perfect. So this is going to be this one. Okay. Then it's not going to be bromine on the top here, but the methyl group will be on the top. So the negative charge will be gone because they're going to use the electrons in the lone pair, and the positive charge will be gone because there'll be electron donated to that carbon. So it looks like this. Not bromine. So it's actually pretty simple. If you know the plus and minus kind of opposite charge. I don't know if you can recall, but this is a Coulomb's law. Positive, negative, they're kind of attracted to each other. But anyway, you don't have to know. So this is something, main common rule you can apply for many polar reactions you'll see in the organic chemistry. As you can see, only thing you kind of need to practice on is try to show the trajectory of your electrons bonding to other, like if it's full-headed and the fishy hole or a half-headed arrow, it can tell you there's radical or polar reactions. This is pretty much it. So I'll just stop here today. I'll do more examples. Oh yes.
So in this example, the bromine, we just kind of discounted.
Yes. So that's a very good question. So this is eventually used up for so this is kind of a, do you remember Lewis acid base kind of thing? So this is more like electron pair donating kind of potential atoms, right? So if there's anything, you have the proton will be bonded to here. So this is more like a Lewis, like a base kind of work. But if you don't see it in the problem, you don't have to worry about it. I normally finish it in the one step. Because if you think about other ones, that'll be too complicated. If you do this, so many steps on the moving is very sequential, right? That is what we call reaction mechanism. Have you heard that? A reaction mechanism? It's all the arrow. But in the exam, I'm not gonna do the mechanism a lot. No, I don't think there'll be too much. So just one step, then you'll be just so. That was a very good question. All right, so thank you guys. I'll stop here. I'll do more on Wednesday, and also possibly I can finish chapter 6 on Wednesday, so we can move on.